Here's like an example from a project that I worked on recently, just doing basically the exact same stuff that we've been teaching in class. So the point of the project was to try to estimate what's the effect of adjusting PEEP settings on mechanical ventilators. That's just basically how much air is left in your lungs after an exhale, on something called driving pressure, which is an overall measure of strain on your lungs. This graph is just based on physiology. It's not based on data. It's what physiology predicts the impact of PEEP on driving pressure would be. It predicts this U shape where up to a certain point, increasing PEEP decreases driving pressure, but then after that point, it starts increasing it. We fit this linear model up here, where delta PEEP is the amount that you change PEEP by. And we also included this PEEP, running mean previous PEEP, this thing called tidal volume, which is another setting, the time after baseline, the previous driving pressure, the running mean previous driving pressure, and we included all two-way interactions. That's what this means between these variables. We had a lot of data, right? We had a lot of observations of patients at different times and the measurements, so we could fit a model with like tons of predictors. So that's what we did. We included like interactions with basically everything that the doctor who we were working with thought might reasonably modify the effect. And then we also included square terms for a bunch of these things. This S of t is a flexible representation of time, so the effect can vary flexibly with time, but it's all just a linear regression. And then we included a bunch of vital signs variables, lab tests, ventilator settings, all at the previous time point, and baseline covariates like, age and demographics and what ICU unit they were admitted to. And then we used this regression. This is one plot that we made. We just took random people and took their covariates, and each dot is what their expected driving pressure would be, keeping PEEP set at what it was. The x-axis is what this person's PEEP really was, and the driving pressure is where it was predicted to be at the next time step if it remained constant. And then the line shows what our model predicted would happen, give you decreased PEEP to this side, to whatever the x-axis label is, or increased. And like you can see that U shape in these individuals that was predicted by physiology. So these are all people who had prior driving pressure equals 12. All people had prior driving pressure equals 9. Okay, and then the other thing we did was we looked at subgroup effects and got confidence intervals through Bootstrap. So each line, each dot with a confidence interval around it is a subgroup effect with a Bootstrap confidence interval, just like we just did. So this is the estimated effect of increasing PEEP by 2 on people whose previous PEEP was 5 and whose previous driving pressure was 9. So that's a subgroup, right? And same for each dot in each of these plots. So we took a whole bunch of resamples of the data, refit that model a whole bunch of times. And for each refit model, we estimated the effect in everyone in this subgroup of increasing PEEP by 2. And then we took the standard deviations, added to each effect estimate. And you can see that at lower PEEPs, the effect of increasing PEEP is to decrease driving pressure. But then as PEEP gets higher, the effect of increasing it further becomes less, which is again consistent with that U-shaped curve from physiology. Okay, so it's just an example of doing basically the exact same stuff from class. Yeah, but that I can talk about because I did it, and maybe it's slightly fancier, the model, but it's the same basic idea.